Hi Calc 2 students, it's me again. During the first week of class, in essence, we've been working on sections 5.3, 5.4, and 6.2, and this is primarily review. The idea is we look at properties of the definite and indefinite integral. We recall the fundamental theorem of calculus. So hopefully at this stage, my goal would be that you could calculate each of these quantities. This is a definite integral, that's a definite integral. That means whatever this worked out to be, it would be a number, as with this. This is an indefinite integral, as is that, as is that, as is that. Now, this we can easily anti-differentiate simply using our list of known antiderivatives. The result would be 1 over the natural log of 2 times 2 to the x. This function, we could break things up and use the rules for constants, pull them through the integral sign, and this would not be too difficult to do either. I'll let you verify that it would be 4x plus 3 e to the x plus our arbitrary constant c. Now, for this one and for this one, we have to do a little bit of algebra first. So we would expand this and simplify, and we'd have to use properties of fractional exponents to simplify this as well. So the first thing we try to do when computing an indefinite or definite integral is we try to find an antiderivative using the functions on the list. If that doesn't work, then we might have to do some algebra to simplify. Now, the goal of this section, 6.4, which is coming next, is to cook up functions, cook up antiderivatives for functions that are hard. So for example, let's say we have f of x equals 1 plus x to the third, the square root of that. Or let's suppose that we have e to the x squared, or the sine of 1 plus x squared. In the lab, the first week of classes, we'll actually be using Wolfram alpha and trying to conjecture what antiderivatives of these will be, and we won't be able to find one. So these are functions whose antiderivatives are just beyond our current means. In fact, it's pretty much impossible to compute antiderivatives using the methods that we'll talk about later in the class. So what we're going to do is we're going to cook up an antiderivative using a special tool. Here's a simple example. This function doesn't have a formula per se, but it's piecewise linear. It's equal to constant of 2 up here. It's 0 right there. Now, this is a nice function because we have triangles and we can compute areas. That's why I wanted to look at this one first. So, we have a new function, capital F of x, and we're going to define it to be a recorder of area. We sometimes call it an area accumulation function. Whatever x is, we look at the sine area between the graph of little f, the horizontal axis, starting at 0 and going up to x. So let's take a look at an example, and then I'll explain why we don't use x as the variable of integration. Let's say we try to compute f of 1. Then the rule for the function says substitute 1 in for your upper endpoint. So we want to compute the compute the definite integral of the function little f from 0 up to 1. And that's nothing more than this signed area here, which is the area of that rectangle, or in other words, 2. Capital F of 0 is the integral. We plug 0 in for the upper endpoint, the integral from 0 to 0 of little f. Well, there's no area to compute because these two endpoints are the same. So that's 0. Capital F of 2. We plug 2 in for x up here, which means we plug 2 in for x up here. That means we're computing the signed area between the graph of f, the horizontal axis, 0 and 2. Let's go up and take a look at that. So we're taking this area and we're adding on this area. So we have the original 2, plus the area of this triangle, which is 1/2 the base times the height. The height is 2, so the area of that triangle is 1. So that means that capital F of 2 is equal to 3. So again, the way capital F works is that it adds up area. Now, we don't use x as the variable of integration. We use something besides x because we're reserving x to be the input of capital F, which means we're going to put it right here. It wouldn't make sense to say from x equals x, x equals 0. So we need to use a different variable of integration. The fact that I use t here is not important, but it just has to be something other than x if I use x there. So it could be from s equals 0 to s equals x. If I used s's here, I would still get a 2. If I used s here, I would still get a 0. That's important. Let's do a couple more examples. The integral. Looking at capital F of 3, that would be the recorded area between the graph of little f. So go from 0 up to 3. So let's go back and take a look at the graph. Well, we've already done the area from 0 up to 2, and there's no area to add on here. So this is going to be the same as that area right there, which was capital F of 2, and we already recorded that. It's equal to 3. Capital F of 4. So we're looking at the signed area between the graph of little f, the horizontal axis, 0 up to 4. Now this triangle has an area of 1/2 the base times the height. Well, the height is actually equal to 2, so this has an area of 1. But the graph is below the axis, so we're going to have a 2 plus a 1 minus a 1, which is a 2. Capital F of -1. Now notice how we have endpoints which are in the unnatural order. So we can change this by switching the order of the endpoints. Which means now we want to look at the signed area between the graph of little f, the horizontal axis, -1 and 0. Let's go back here. Well, the area of that triangle is 1/2 the base times the height, which is still going to be 1. However, because of this negative sign, the result is -1. I would like for you, on your own, outside of class, to compute capital F of -2, capital F of -3. This is something you need to do for the next class period. Now we can make a table of values. -3 and -2 I'm going to leave blank because I want you to fill those out. In other words, we're going to take all of these results, we're going to plug in the x value, and we're going to write down what the result was. F of -1 was -1. So I'll put a -1 there. Capital F of 0 was 0. Capital F of 1 was 2. Capital F of 2 was 3. And we didn't do F of 3 or F of 4, but those would be fairly straightforward to do as well. So that's how the area accumulator function works. So we can see right now, take a look here. How are the values here changing with the values there? That's what we want to keep track of, and that's what we're going to look at during the next class period. We're actually going to discover that this area accumulator function, as ugly as it is, even though it involves an integral sign, it actually will be an antiderivative. So that's the goal of the next class period. So again, what I want you to do is I want you to compute capital F of negative